In this lesson, we're going to have a look at using the discrete probability distributions to include the binomial distribution. Let's take a look at an example. 3 bulbs are planted in the garden. The probability they produce a red flower is 0.3. Given that all 3 bulbs grew and produced a flower, and that they are independent events, let's draw a tree diagram to show the probabilities for all of the different possible outcomes. So the idea here is that we are either having a red flower or not a red flower, so that is the red prime or red dash. And we have 3 bulbs, so we've got 3 sets of branches along this tree diagram. The probability of a red flower is 0.3, therefore not red must be 0.7, so we can pop the probabilities on each of the branches. And we can then work out the outcomes, so getting 3 red bulbs would be 0.3 times 0.3 times 0.3, and that would give us 0.027 as a probability, and we can work out all of the other probabilities in a similar way. Now we can translate this into a discrete probability distribution, and so the capital X notation that we used in the previous lesson can be denoted by the number of red flowers. We can then find the probability distribution of X, and we can pop this into the probability distribution table. So we can take a look at what are the outcomes of this event. You can either have 3 red bulbs, 3 red flowers, 2 red flowers, 1 red flower, or 0 red flowers. And we can then have a look at all of the probabilities of these as well. So there is only one way of getting 3 red flowers, and that's the first probability there. If we want 2 red flowers, there are 3 different combinations here, and we need to add those 3 probabilities together. To get 1 red flower, we have another 3 possibilities, add those together, that gives us 0.441. And there is only one way that we can have no red flowers at all, and that's the bottom probability. Let's take a look at another example. So what happens if we have 4 bulbs planted in a garden with the same probability of a success of getting a red flower being 0.3? So the probability distribution this time, if we look at the table rather than the tree diagram, there's only one way of getting 4 red flowers. Each probability is 0.3, so we multiply 0.3 by itself 4 times, and there is only one combination. This gives us a probability of 0.0081. Now that can be written as 0.3 to the power 4 times by 1. If we're looking at 3 red flowers, there are 4 different combinations now. And so we are multiplying 0.3 by itself 3 times. It says 4 down here, but that should be a 3. And then we also need to multiply by not getting a red flower, which is 0.7. So we have the probability of getting 3 red flowers is 4, that's the number of combinations, multiplied by 0.3 to the power 3, that's the getting the red flowers, and then multiplying again by 0.7, the probability of that last flower not being red. And this gives us a probability of 0.0756. We can repeat this. So looking for the probability of getting 2 red flowers, there are 6 combinations. We multiply that by 0.3 to the power 2, and then multiply that by 0.7 to the power 2. So it's the probability of the success and the probability of the failure of not getting that red flower. And what you should be noticing at this stage is this is the way that we calculate binomial probabilities. We can do the same thing again. Now, fortunately, we're going to be using our calculator very shortly to work all of these out, but this just shows you where these probabilities are coming from. Now, let's have a look at what would happen if we repeated the same idea but for 5 bulbs. Same idea again, so the probability of x being equal to 5, 1 times 0.3 to the power 5. probability of x being equal to 4, so 4 red flowers. We've got 5 combinations. Probability of a success 0.3 to the power 4, and then the failure 0.7. And you'll notice as we go through this, this is just the binomial distribution. These numbers at the beginning are the number of combinations, and we can find these out using the NCR button, just like we did on the binomial chapter. Now you can use your calculator to work out the number of combinations in a couple of different ways. So you've got your NCR button just above the divide symbol on your calculator. And there is a formula for this as well, which is n factorial divided by r factorial multiplied by n minus r factorial. And this factorial button symbol means, in the case where you have 5 factorial, it means 5 times 4 times 3 times 2 times 1. So it's the product of all of the natural numbers, the positive integers, down to 1. And so if you were working out 10c3, which we would write as 10 over 3 inside of a bracket, that would give you 120. And this is used a lot when you're looking at statistics and probabilities. So this example here, if you had 10 prize boxes to choose from and you pick 3 of them, how many options do you have? You have 120. So for your notebooks now, this is the features of the binomial distribution that you need to know, learn and understand. So a discrete random variable is distributed binomially if it fulfills the following conditions, and it must fulfill these in order for you to be able to use the binomial distribution. So the first one is there has to be a set number of trials, and these are things that you need to be looking out for, certainly within wordy questions. There has to be only 2 outcomes, either a success or a failure. That's the binomial part of this distribution. Each trial has to have exactly the same probability of success. They have to be independent of each other, which is the next one there. And then if all of those 4 things hold, then the binomial distribution can be written as, and we have this capital X, and we say it's distributed, that's the little tilde sign, with a capital B and N and P inside of a bracket. The X is representing the random variable, that's the event that is occurring. This is telling you how it's distributed. The B is telling you the distribution is binomial. N is the number of trials, and P is the probability of a success. For the next few slides, I'd like you to have a go at trying to work out whether each of these events are binomially distributed, and you need to consider those 4 different situations that we just looked at that you wrote down in your notebook. Decide yes or no and see if you can justify your answer as well. So the first event, a dice is rolled up to 10 times, and if you roll a 6 and you win, and then you can stop rolling. This is not binomially distributed. And it is not distributed binomially because there is not a set number of trials. It could be anywhere between 1 and 10. It would only be a binomial distribution if you said, regardless of whether you got a 6, you still have to roll 10 times. Apples come in bags weighing exactly 2 kilograms. Every apple is checked in the bag to see if it is bruised or not. Is this a binomial distribution? No. There is not a set number of trials, as a 2 kilogram bag could contain any number of apples. A buyer's coin is thrown 20 times and the chance of getting ahead is 0.1. The number of heads is recorded. Is this binomial? Yes. If we were to write its probability function, it would look like this. X is distributed binomially with 20 and 0.1. In a pack of 12 eggs, the probability an egg is broken is 0.02. Is this distributed binomially? Yes. Exactly 12 trials, eggs are broken or they are not broken, and the distribution is written below. A class contains 10 girls and 15 boys. A team of 3 is selected at random from the class and the random variable is the number of girls on the team. Is this binomially distributed? No. Why? The probabilities are not independent. As soon as one class member has been chosen, the probability of choosing the next class member will be dependent on who was taken in the previous selection. A football team plays 20 matches against different teams, and the random variable is how many wins the team gets in total. Is this distributed binomially? No. It is not the same probability, as each of the teams will have a different ability. A spinner has 3 different colours, red, blue and green, each with an equal chance. The random variable is how many times you get a blue if you spin it 10 times. Is this distributed binomially? Yes, and this is the distribution. So back to your notebooks. Here is the binomial distribution. To calculate a probability for the random variable x, we can use this formula. So this is just the same binomial distribution that you've looked at in the pure part of the course. The first part is the probability the random variable x is equal to a given value. We then have the number of combinations of x successes out of n trials. We have the probability of a success raised to the power of x, the number of the value given, and then we have 1 minus p, which is the probability of the failure. And this probability function is in the formula book. Here's an example for your notebook. Terry sends out 20 invites to his friends for his party, and the probability that his friend will accept the invite and will turn up to a party is 0.18. The number of people that turn up to Terry's party can be modelled using binomial distribution. Find the probability that A, there will be exactly 5 friends that turn up to his party, and B, that at most 2 friends turn up to his party. And then we'll take a look at the assumptions that need to be made in order for this to be modelled with a binomial distribution. So the first step is to identify the number of trials, that is the number of invites that have been sent, so that's 20, and the probability of a success, which is 0.18. Now we're going to answer the first question, the probability of exactly 5 friends turning up to his party. This means we need the probability that x is equal to 5, and we can use the formula which is written down here, but I would definitely recommend that you use your calculator to be able to calculate this. So you will need to go through the calculator process for this question. And this gives you a probability of 0.149. And that is a probability, if we turn this into a percentage, of 14.9%, but you can leave a probability as a decimal as well. For part B, we have the probability at most that 2 friends turn up, so this is x being less than or equal to 2. Now there are a couple of different ways that you can calculate this, so you can calculate x equal to 2, equal to 1, and x is equal to 0, and then add them all together. But on your calculator there is the cumulative distribution function as well, which may be a little bit quicker for this question. So working out those 3 probabilities, adding them together, this gives us 27.5%. Now the assumptions that need to be made, and this is quite a typical exam type of question, so you do need to learn those 4 different things for the binomial distribution, the sort of the rules if you like. So we have the probability that each friend turns up is independent of each other. The probability each friend attending is exactly the same. Only the 20 people attend, so that's the fixed number of trials. And you can choose any one of these. So it says the model is probably not binomial, as it's unlikely that all the friends have equal probability of going to the party, and they are probably not independent. But if we make some assumptions, we can loosely work out what the probability would be, but there may be other distributions that could be a better model for this situation. If you pause the PowerPoint here and just access the PowerPoint on how to use your calculator before continuing on, and then you can always refer back to the help for the Casio calculator throughout the rest of the exercises that you need. So we'll keep this separate to the actual learning of the topic. So let's take a look at this example. Given the random variable x that is distributed binomially with 15 trials and a probability of success of 0.1, I'm going to work out the 4 different questions below. Now it's useful to use a number line with these, especially when you're looking at inequalities and less than and greater than, and sometimes with the mixture of both. So taking a look at the first one, we have x is equal to 4, so we only want one single probability here. Now it's best to use the binomial PD function at this stage with the value of, let me just write this on here as well, so this is your n, this is your p, this will be your x value, and you're using the binomial PD function. It doesn't matter whether you use the list or the variable, you'll be able to get to the same solution. For the next one, x is less than 3, so be really careful with the strictness of the inequalities. So we want 0, 1 and 2 for the probabilities, and we can add these up separately. So that if we use this method, then again this is the same binomial PD function that you would need, but you can use the binomial CD function as well for this question. If you're using the binomial CD function, then you would be looking at the probability that x is less than or equal to 2. For the next question, we have x is greater than 3, so we would like all of these probabilities added together. Now we can do that, we can add up all of those individually, or we can do 1 minus the probability all of the values lower than 4. Just checking that's right there. Yes, because we want x is greater than 3, so we need to take off the probability of 0, 1, 2 and 3. And again, if you wanted to, so if you've got the equals probabilities here, then you're using the binomial PD function, but you equally could be solving this question using the CD function as well, and that would be 1 minus the probability that x is less than or equal to 3. And then for the final one, I'll just remove the writing on here. So identify the values that you need first of all. So we have between 3 and 5. It includes 3 but does not include 5. So actually we only need the probabilities of 3 and 4. Nice and easy for the PD function. There are only 2 here to fill in. But equally you could be using the CD function as well. So there are ways of using both functions, and you can flip between the two within a question and still come up with the same answer. So have a go for yourself, see if you can come up with the same results. So when you're using your calculator to find probabilities, you do need to bear in mind the different type of question that may be asked. In general, you'll be using the binomial PD function if you have a question that is of this form, the probability of x being equal to a. So it's an equals that you're looking for there, the equal a. You would use the binomial CD function if you have an inequality within that bracket, but there are ways in fact that you could use the PD function even if you do have a less than or a greater than symbol as well. Now there are some other things to bear in mind here. I'll just run through these fairly quickly, but it is probably more useful to take a look at how to use your calculator with a specific example, as I think it's more clear, but these are the general results that you may like to copy down. A biased dice has the probability of 0.4 that it lands on the number 3. If the dice was rolled 100 times, how many times would you expect it to land on the number 3? Well, this is a binomial distribution, and if you rolled the dice 100 times, you would expect there to be 40 times that it lands on the number 3. So when you see this expected value, sometimes you may see this as the mean as well. So if you see mean or expected value, this means the same thing. And there is a generalized form for your notebooks on the following slide. The mean of the binomial distribution can be calculated using the formula n times p, and the variance can be calculated using the formula n times p times by 1 minus p. Now we can use the variance to calculate the standard deviation by taking the square root of this, and all of these formulae are given in the formula book. Please complete the exercises listed on this slide. You must be able to use your calculator in order to complete these exercises, both the binomial PD and CD functions, so make sure that you have gone through the process for that. There are some hints on the following slides of how to complete the exercises that were listed on the previous slide. Now for exercise 2.4, which is on page 189, you will need to use your calculator for all of these questions, and I would suggest that you use the PD function for these questions as they are all equal to, and for these ones I would recommend the CD function, but you are also welcome to use the PD function as well. If you've watched the slideshow on how to use your calculator, you'll see that there are different ways. Sometimes it's easy to use the CD function, sometimes the PD function. And question 3, that's one where you're going to have to work out whether it's the PD or CD, depending on what the question is asking you for. Now exercise 2.5, which you will find on page 190. Very similar to the last one. Lots of different questions here. They look mostly like they're going to be the CD function with them being inequalities, but there may be some a little bit lower down where you have an equal to, so that could be the PD function there. And you're also given some other pieces of information. So the mean, remember the mean is n times p, so you may need to be able to work some things out backwards in order to solve this problem. So you're not given the value of p in this question, so it's a bit more of a problem solving style question. And for this exercise 3.1, which is on page 192, again very similar. Most of these look like they will be the CD function. Just be careful on the strictness. Is it less than or equal to or just less than? If it helps, use a number line. So you can see here where you've got 10. That means you have outcomes from 0 to 10 all the way up. So just have a think about what does it mean if you're looking for the probability that x is less than or equal to 2. That means that you want all of these 3 things, but your calculator can do a lot of these things too. It's the main thing here is just making sure you take a bit of time in considering whether some values are included or not included when you're working out the answers to these questions. Exercise 3.2 on page 193. Very similar again. These look to be mostly greater than or equal to, so that number line again does come in handy. So if you've got all of your outcomes from 0 to 15, and for this question here you want x being greater than 3, so that means it does not include 3. You want all of these. Now you've got to work out, is it easier to work out the probabilities of this larger section, or is it easier to work out the probabilities of the smaller section? And a number line is a nice easy way of being able to sort of picture what's going on here, but all of these questions you definitely need to be using your calculator for. And for exercise 4.1 on page 195, much more written question. So with these you're going to have to say how x is distributed, working out the number of trials and the probability of a success. And you are then having to read a question really carefully. So it says more than 4, greater than 4, exactly 10, x is equal to 10. So you do need to read the questions carefully, especially again with that strictness. Is it greater than or equal to, less than or equal to?